Hello and welcome. My name is Mohammad Afzal Shadab, and I'm a future faculty in physical sciences postdoctoral fellow. In this video, I will talk about constructing solutions using unified kinematic wave theory for melt infiltration into Firn. This video is a companion to our recently published work on uh, on this topic in Journal of Glaciology, and it's an attempt to make the solutions accessible to the community. So thank you so much for your interest in this work. Let's begin with a short introduction to unified kinematic wave theory. Kinematic wave theory is a framework to describe propagation of waves, in this case, waves of melt, and that is influenced by the motion of particles rather than the force acting on them, the motion of fluid particles specifically, and rather than the forces such as pressure acting on them. I call it unified framework because it's not derived from prior kinematic wave theories, but it still unifies most previous work, as you would see in this presentation. And it also extends to perched aquifers where the original governing equations do not satisfy this wave nature. And this extension was made possible using Shadab and Hess 2022 water resources research paper. So in practice, kinematic wave theory is restricted to hydrology, but the more general term is method of characteristics. This is a method where we find curves along which a complicated governing equation, we call it partial differential equation, reduces to a simplified governing equation or an ordinary differential equation, which could be solved easily. So moving forward, I'll begin with some fundamentals to this theory, starting with defining the system. The system is a three-phase system. Here you're looking at a CT scan of wet snow at a millimeter scale, where the blue color refers to the solid ice crystal, red color refers to the liquid water, and the white regions are the air gaps. This three-phase system has several assumptions that we use in this work. And first assumption is the density of liquid water is the same as density of ice, which is about 1,000 kilograms per meter cubed. There is no heat conduction in this case from non-dimensional uh, analysis. We found that the heat conduction is about 1,000 times smaller than heat advection or the heat carried through motion of water. What it means is wherever there is heat transport, there has to be a motion of melt or percolation of melt in the porous medium. Next, we make the simplification that there is no interfacial tension in between liquid water and air at the solid crystal interface. This simplification helps to make the flow only gravity driven or pressure driven rather than capillary pressure driven. Next, we assume that the local thermodynamic equilibrium is in effect, which means if I make a box and call it representative elemental volume, where things are averaged, in that box, if there is any phase, be it liquid water, solid ice, or air, they will have same temperature. And that would be the melting temperature if all three phases exist. Lastly, we assume that the residual water saturation is zero, which is correct in the case where we are imbibing into a porous medium, since water wets the ice. However, in the case of drainage, that is a positive value. Furthermore, if we make these assumptions without going into the math of it, we are left with two dimensionless conserved variables called composition and enthalpy. Composition is just the total amount of water in any box or any representative elemental volume. And that total amount of water is the volume fraction of ice in this region, which is just the volume of this blue region divided by the volume of the box or bulk volume. We call it phi sub I. And liquid water content, which is um, the fraction of volume of this red region, LWC or phi sub W. Next, the conserved variable is enthalpy. And enthalpy is dimensionless composition times specific heat of ice at constant pressure times the temperature minus the melting temperature divided by the latent heat of fusion of water given here. And that is the case when temperature is less than melting temperature or no liquid water is present in the domain. And enthalpy is less than zero. But if enthalpy is greater than zero and less than this maximum enthalpy before which all of the ice melts, the dimensionless enthalpy is equal to the liquid water content. And this comes beautifully from the non-dimensionalization of this physical system. Next, I have also mentioned the porosity, but it's not a conserved variable. Porosity is something we deal with regularly. Porosity can be written as 1 minus dimensionless composition plus maximum of dimensionless enthalpy and zero. So in cold regions, this is just 1 minus dimensionless composition as enthalpy is always negative. But in temperate region, this term will be smaller. So it will be 1 minus composition plus dimensionless enthalpy. Now, let's talk about the problem that we could solve with this framework. And to do that, we just need to define all the other state variables in the system. In this case, from dimensionless composition and dimensionless enthalpy, we can mention the temperature or other state variables such as liquid water content. Here I'm plotting the dimensionless temperature as a contour plot, which is temperature minus melting temperature, 273.16 Kelvin divided by melting temperature. So we just non-dimensionalized it. So wherever it is zero, it means the temperature is the melting temperature, which is the three-phase region where the Firn is temperate or even slightly saturated. But below this, in this region, we do not have liquid water. In cold region where enthalpy is less than zero, the temperature is less than zero. In that region, there is no liquid water. On your right, you're looking at the liquid water content. So again, from composition and enthalpy, we can plot everything else, every state variables. In this case, for composition equals zero, it means all gas. So if you think about a box or a representative elemental volume in that REV, there is only air present. But if you increase the composition, now there is some water, and that water could be solid or liquid. But in this case, since the enthalpy is zero, we are only having solid water. So here, think about a chunk of ice with no air, no water in it. Now, if you put this on a Bunsen burner, ice will start to melt and the temperature will stay the same, 0 degrees Celsius, but the enthalpy is increasing slowly. And you can also see that the liquid water is generating because of the phase change. All that energy goes into the phase change. And that is one of the reasons, or the primary reason, why we picked enthalpy as the primary variable and not the temperature. Because if you look at temperature in this region, there's no change in temperature if you go from this point to that point. But there is certainly a change in enthalpy if you go from this point to that point. And at this point, we have maximum water and maximum water. So the liquid water content is just 99 or 100%. So um, we do not have ice at this point. Here we have liquid water and air only at this point, but that also has some air in it. Next, we are interested in dimensionless flux since we are talking about transport of heat and water. What we need is a flux, and that flux comes from a simple relation which is identical for composition and enthalpy. And that's the beauty of scaling analysis, where the flux of composition is the same as flux of dimensionless enthalpy. So here I'm plotting that flux. That flux is zero below the enthalpy equals zero line, because there is no liquid present. And if there is no liquid, nothing will move. But if there is some liquid present, that liquid in this Firn, that liquid can move down. And as it goes down, it carries its latent heat with it. And it can change the enthalpy of this region in the next instant. So these are directly connected and these are identical, the flux of composition and enthalpy. And these are lines of constant flux, and the flux increases as you go up and up and up because the liquid water content is increasing as you go from this point of no water to all water region. So thinking about this, the big picture takeaway is from composition and enthalpy, we can make all the state variables. And furthermore, it gives us much more than just plotting the state variables. Thinking about simple problems, we can use this unified kinematic wave theory for solving simple initial value problems. So think about a Firn where you have two states. On the top, you have one state in Firn, and on the bottom, you have another state in Firn, and there is a jump. We call such problems as initial value problems. We can plot these by plotting them on this curve called hodograph plane. Hodograph plane is a vectorial representation of movement of body or a fluid. In this case, movement of melt through the Firn. If you look at this plot, you will see two types of curves. One is these dark dashed lines called slow path. Slow path are the lines of constant flux or meltwater flux. And the uh, fast paths are the lines of constant porosity in the three-phase region. So what we do is we basically uh, plot the points, plot the state points corresponding to top and bottom states, and then we join them somehow from the rules of it. And the rule is you always start with the slow path, and um, if there is no saturation, then you start with the slow path, and you end with the fast path if there is a need to go on the fast path. So we also have something called extended path. For example, if we have any state in this region, in the cold region, there are no characteristics there per se. But in that special case, the characteristics or these lines, integral curves is the technical term for it. They can be extended into this cold region, and we call them extended path. And once we sketch this, that is really our solution. We just need to extract the physical quantities out of it. Let's begin this with a simple case. The case where the Firn is temperate. So it's equivalent to temperate soil um, if taken at face value. We call it three-phase region. Let me So the first case is of steady melt water flux in temperate Firn. Think about a Firn where the liquid water content is 40%. So your H from the relation we talked about in previous slide, few slides back, that leads to H of zero point 0.4, and the porosity is 70%, which is 1 minus C plus H in the temperate region. In cold region, it's just 1 minus C. So 1 minus 0.7 plus 0.4, it comes out to be 0.3, 0.7. And that is what we have here. That is our left state or our top state. Okay, so this is that. And then our bottom state is 45% liquid water content and composition of 0.895. So that means we have a porosity of 1 minus about zero point 0.9 plus 0.5, which is close to 0.55. So 55%-ish porosity and 45% liquid water content is our bottom state. And how will the system evolve? The simple solution is you just connect them, by a simple line on the slow path. The characteristic or the information of on slow path is stationary, it does not move. The wave do not move. That is a linear degenerate wave called contact discontinuity, where the flux stays the same. The meltwater flux stays the same on the side. So the solution can uh, then be made in this plot showing the dimensionless velocity on the y-axis, and then on x-axis you have dimensionless composition and dimensionless enthalpy. And as I said, there is this dimensionless velocity, which is the ratio of dimensionless depth to dimensionless time. Since these are self-similar solutions, you can multiply this with different times and get the solution at all those times. But interestingly enough, in this case, the wave does not move. It stays at its initial location. And that means even at later times, it does not move. So here, this is your left state, again, plotted here and here. And then this is your right state, plotted here. And they are just connected by the stationary wave called contact discontinuity C, which does not move. And physically, if you look at the volume fractions of gas phi sub G, liquid water content, phi W, and ice volume fraction, if you use that, this is how it looks, where you have 70% porous Firn, and which is about 40% saturated, above 65%-ish porous Firn, and where you have 45% liquid water content. So all it's happening is you have a Firn, and on the Firn there is a change in porosity, but there is no change in meltwater flux. So the water is just steadily going from top to bottom. So that's what this curve is representing. You are changing the porosity, but you're not changing the meltwater flux. So this is the solution, and it's a very simple case of a contact discontinuity. Next, we move on to a more complicated case where, again, we have the same Firn, which is 70% porous and 40% liquid water content. This is our left state or top state, and our bottom state is this 55% liquid water content, more saturated. So it has more liquid water content in the bottom, and then the porosity is the same because these are on the line of same constant porosity. right? So for that fern, the solution is very interesting as the speed of waves increase as you go towards the top. In this direction, the speed of the waves increase. And if you go down, the speed of the waves decrease. So in this case, it results in this self-smoothing front called a rarefaction front or a drying front. So this drying front comes in between these two state points. So this is your top state and this is your bottom state. And these are connected by this self-similar drying front. Again, this is in self-similar variables, dimensionless velocity. You can also see that this point is also moving. So it's not like the tail end of this rarefaction wave is stationary. It's also moving. It could be stationary, but in this case, it's moving. And to calculate this, we just need to calculate the value of the speed evaluated at this point, 0.7 and 0.4. And since we are on second integral curve or fast path, it has to be lambda 2 evaluated at this point. So that will give you this particular point. And you can see that in the code published on GitHub. Physically speaking, it looks like this, where you have Firn of 70% porosity all the way across, but there is a reduction in melt flux. So earlier the Firn was more saturated, but after some time the meltwater flux stopped. So one might imagine that this chunk of block will just go down as it is, but in reality, due to the wave nature of Firn or of meltwater in this porous medium, it does not go down like that, but instead it goes down like this self-similar drying front, and it goes down with time. This is dimensionless time. Again, if you are interested in how this is being non-dimensionalized, that's where we have defined the dimensionless time and dimensionless depth to make things general. So this is the case where meltwater flux decays. Next is the case when meltwater flux increases with time or wetting happens. So in that case, we have taken the same for 40% liquid water content and 70% porosity. And in this case, the right state or the bottom state is 20% liquid water content, and 1 minus 0.5 plus 0.2 is 70% porosity, since we are on same porosity line. So 70% saturated, but 20% liquid water content, so less saturated. So the bottom is less saturated, this is more saturated. So the meltwater flux has increased. In this case, we are supposed to connect them along the fast path. We do not go on any other path. We connect them on fast path. And this, as you go from left state to right state, the speed of the characteristics decrease, which means they would lie on top of each other, which is unphysical. So in this case, it results in a wetting front or a sharp front that moves at a characteristic velocity. So if we plot the solution of dimensionless velocity, here you could see that the left state is here and the right state is here, and they're connected by this uh, moving wave front called wetting front or shock wave. This shock wave S is moving at a constant speed, and that speed can be calculated by a discrete mass balance called Rankine-Hugenoid jump condition, discrete mass balance of water or discrete enthalpy balance across this wave front. And this line is then called Hugenoid locus. Now, in physical sense, it's again the 70% porous Firn from top to bottom. In the top, you have a higher saturation. In the bottom, you have lower saturation. So melt flux has increased. And you see that over time, this wetting front moves down with a constant speed. Next is the case when these left and right states do not strictly fall on the same point. So the left state and the right state cannot be directly joined, since they do not fall on the same curve. So in that case, we have to use uh, both of these paths, slow path and fast path. So for example, here the left state or the top state is 10% liquid water content, and 1 minus zero point 0.3 plus zero point 0.1 is 0.8, 80% porosity Firn. And the right state is more saturated and um, less porous Firn. So in this case, 1 minus 0.948, which is almost zero, and then uh, zero point 0.5. So this is 50% porous. So more porous this case, less porous this case, but that doesn't matter. What matters is the liquid water content is decreasing as you go from top to bottom. Here it's less liquid water content. Here it's more liquid water content. So in this case, we are dealing with two things. We are dealing with change in flux. We are dealing with change in porosity. So that change in porosity leads to a stationary wave called contact discontinuity. So from top, the solution in this case, the solution in this case is you first go on slow path or on the line of constant flux, because that is a jump in porosity, and that porosity jump does not move. And then you make a slow path from the left state, and then you make a fast path from the right state. And wherever they join is your intermediate state. So you are forming a new state called intermediate state in between the left and the right state. So in this case, intermediate state is slightly higher saturated, but it will have same porosity as your left state. But the composition is the is the same. It has the same porosity as the right state, my bad, as they fall on this line. So the solution in this case is from left state in composition I'm showing, and similarly you can show it for enthalpy. From left state, there is a stationary wave called contact discontinuity, C1, which stays right at the jump. And that is a change in the porosity wave. And then you reach to this special or a new region called intermediate state. In this state, your composition has increased, your enthalpy has increased. And then from the endpoint, this endpoint can be calculated very easily by calculating. So you just calculate the lambda 2, or the speed of the wave or the characteristic at this tail end, when intermediate states variables are known from this hodograph plane exercise. And you calculate that, and it turns out to be this point. And from that point until this point, you go from this region to that region in this direction. So you go in this direction, and then you go in that direction, again this direction, and then this is your rarefaction wave or your drying front. And then you reach to this point, which is your right state. All of this is your right state. In physical sense, it leads to this solution where you have initially there is a change in porosity, step change in porosity, and there is a reduction in melt flux. So that step change in porosity stays right where it happened, but change in meltwater flux leads to this moving nonlinear, genuinely nonlinear wave called drying front or rarefaction wave, and that spreads. It's a self similar smoothening wave, which spreads over time. So the water just does not go down as a chunk, but instead it goes down as this nice sort of wave. And this is a straight line because of the parameters we chose, m equals 3 and n equals 2. If you choose a different parameter, this can come out to be some weird shape, which we are not talking about today. Next, what happens when there is a change in porosity? Yes, at the jump, as well as a change in meltwater flux. So what if the meltwater flux rises with time when there is a change in porosity? So in this case, this is your left state. For example, these are all examples. You can construct your cases in a similar fashion. So in this case, this is your left state. Again, about 50% saturated and about, 50% liquid water content and about 50% porosity. So almost saturated. So C equals 1 is your line of complete saturation. So it's very close to getting fully saturated. And then your right state is this dry Firn. In this case, rather than going on the path shown on the previous slide, you cannot go on fast path first. You can only go on fast path if the situation is more complicated when the region is fully saturated. But in this case, you cannot. You first need to go on slow path. So make a line from the left state, make a line along the slow path, and then from the right state, sketch a line along the fast path. And wherever they intersect, in this case, they're intersecting at about 45% porosity and about 1 minus 0.648 plus 0.448 is the porosity. So the porosity in this case is 80%. So 80% porosity, since they lie on the same line and it has same porosity as the right state. So the solution in summary is from left state, there is a contact discontinuity which stays right at the point of the jump, signifying the porosity jump. And then from that intermediate state, there is a fast path, which is your shock wave. We are not going in the direction where the speed of the waves increase. So it's not a nice and smooth solution, but instead we go on the opposite direction, again in the similar sense as a shock. So we go along Huguenot locus, and that leads to a shock wave in between these 2 points, which is the intermediate state and the right state. And that is how it is plotted in this diagram. From left state, there is a stationary contact discontinuity. And then in between intermediate state and right state, there is this line. This line, so C1, and this is shock wave, so S2. And that shock wave is moving down at a characteristic speed, which again, you can use Rankine-Huguenot jump condition between intermediate state, here calculated from this hodograph plane, and your right state. And you will know how fast this wavefront is moving without running a computer simulation. So moving forward, we think about case where rather than this point, what if uh, our left state was here and the right state was here? In that case, you cannot go on slow path and then go on fast path because you only can go up to C equals 1. You need to go here and then along the slow path and then draw the fast path, which is not physically possible because the hodograph plane only goes for C less than 1. So that gives us, so in this case, you can see that a wetting front move downwards with a constant velocity, and then there is a jump in porosity for the previous case. So let's move forward with this and have our next case where these two could not be connected directly, right? They can if we could have gone above C equals 1, but that's not possible. This theory is only for C less than 1. So we use Shadab and Hess to actually go beyond beyond a special sort of hyperbolic partial differential equation framework. In that case, this is your left state and this is your right state. You cannot plot your slow path up to this point and then extend fast path from that point, and here you have an intermediate state. That is not possible. If that is not possible, it means that you are going to saturate completely. That is a physical representation of saturation if you go uh, up to c equals 1. So in that case, rather than going towards the slow path, you are really going towards fast path. So this is a special case where hyperbolic wave theory fails, and you have to include the effect of elliptic partial differential equation or the effect of perching. So from left state, there is a line parallel to this line of constant porosity along the fast path, and that interestingly is a shock wave, and that shock wave does not go down, but instead it goes up. So it leads to a rising perched water table. So we go up, and then there is this jump because we are fully saturated in this particular region where C equals 1. In this region, um, in this region, there is no wave per se, or the waves move at instantaneously. So here you cannot call it waves, but we call it jump J2. So we have S1 star because it's going upwards rather than going downward like normal wave fronts. And then from this right state, you have another wave S3 or shock wave. So you basically form a form a line parallel to the fast path from the left state and from the right state, and then go extend them up to C equals 1. Once it reaches to C equals 1, you join them. So that way you construct the entire solution. But bear in mind that the flux at C equals 1 is not saturated hydraulic conductivity. In this case, C equals 1, C or dimensionless composition equals 1. In this fully saturated region, the flux comes out from a special formula given in the paper because the flux is not just gravity driven, but instead it becomes pressure driven. So this is an extension we made to this kinematic wave theory. In physicality, it looks like this, where the initial jump was here at this point, but here this is your left state. In composition, right state. Similarly, you have the case for enthalpy, which I'm skipping for now. Um, from left, you go to first intermediate state by crossing this wave called S1 star or rising perched water table. You can see that we have reached C equals 1. So if C equals 1 is reached, which means our hyperbolic wave theory or our method of characteristics fails. And you can see here um, at the initial point where there was jump at dimensionless velocity equals 0, uh, you go from first intermediate state I1 to I2, which is your second intermediate state. And in this second intermediate state, there is a change in enthalpy. There's no change in composition because it's fully saturated region. And that's why we call it jump. We call it jump J2. This is J2. In between this is J2 in between the two cases. And from I2 and the right state R, you have a shock wave or a wetting front that keeps percolating into the Firn. The physical process in this case is this one uh, where you have less porous but more saturated Firn on top of less porous Firn. And in this case, I'm not going into the numbers, but in this case, this huge amount of melt is unable to get into this low porosity Firn. So this wetting front that reaches to this interface, um, that excessive melt is not taken up by the lower layer. And instead, the Firn bifurcates into two parts. It leads to a rising perched aquifer, and that goes up. And at that point, you can still see that the porosity is not zero. We have not completely closed off. Here, you still see a wetting front. So this is your S1 star. And if I erase all this ink, this is your S1 star going up. This is your jump in your porosity at the initial point. And then this is your wetting front S3, S1 star, J2, and S3. And that is your solution. And these values of how fast these are moving refer to the paper for more information. Now let's move on into the cases with cold Firn. In the case of cold Firn, the properties or the formula change slightly from the case of temperate Firn, and we will talk about them as we go along with further cases. So the first case is a two-layered cold Firn with no melt in it. So think about Firn, double layer, and you have this is your top layer, and this is your bottom layer. Top is left and bottom is right. Its enthalpy equals 0, so there is no liquid water, and the temperature is melting temperature, and the porosity is 40%. It's 1 minus C, H is 0, or 1 minus C. So if it is 1 minus 0.6, it's 40%. So it's 40% porous, and temperature is 0 degrees Celsius. However, then you have this case where the composition is 0.8 and the temperature is minus 0.1. And that is the case if you plug it in the formula for the dimensionless enthalpy, it turns out to be minus 20 degrees Celsius, and the porosity is 20%. 1 minus C is the porosity in cold region. So 1 minus 0.8 is just zero point 0.2. In that case, the solution is trivial because there is no liquid water moving, nothing will evolve. So as one might think, the solution is a contact discontinuity between the two. So you just connect them by a line, and they can be any 2 points on this plane, and they can be just combined by this wave called contact discontinuity because that's a trivial solution, nothing changes. So in the dimensionless velocity form or dimensionless depth over time form, um, again we just have a contact discontinuity. All it says is there is a change in porosity and properties like temperature, but there is no evolution because there is no transport of water that carries heat with it. So in that case, uh, the volume fractions for this specific case look like this, where you have more porous Firn on top of less porous Firn. The case could be opposite, but since we do not have compaction in it, the solution looks like this, which is not of interest to us. So in this case, we could not find much interesting stuff. But moving forward with the case where we have cold Firn lying on temperate Firn. So in this case, the top Firn is cold. So think about like a new frozen fringe formed on top of uh, temperate Firn, which is more saturated. So the lower layer is more saturated and is in temperate region. The top layer is less saturated. The top layer is about minus 22.6 degrees Celsius, and it's freshly fallen snow, which is cold. And the bottom layer is 60% liquid water content and 1 minus zero point 0.8 plus zero point 0.6, which is 80% porous. If that is the case, this is your left state and this is your right state. In this case, you first join, we first extend a fast path from the right state, wherever it goes. And when it hits enthalpy equals 0, that is connected to the left state. So from the left state, we form C1, contact discontinuity. And since we go in the direction from this intermediate state I1, we go in the direction of increasing speed of these characteristics that leads to a drying front or a rarefaction wave that goes up. So that is R2. And in that case, the solution is C1R2. Here it looks like this. Now, if we look at the solution in dimensionless velocity form for dimensionless composition and enthalpy given on the x-axis, this is your left state. And from the left state, there is a contact discontinuity right at the jump. And this is your, this does not move. And that is C1. And it leads to a lower composition and a higher enthalpy for this particular case. And just think about this. This right state can be here. And in that case, you just make this line from here and connect it at this point. But the solution would be C1R2 again. And once you reach to this intermediate state here, at that point, um, once you reach this intermediate state, from that intermediate state, there is a rarefaction wave that emanates to the right hand side, and we can calculate that the speed of this tailing end, speed of the rarefaction wave at this point as you go to the top, it's 0. So that's why it's the tailing end is close to the top. It emanates right at the top. It does not move, unlike the case we saw in the previous slides. So this is your solution. This is C1R2. If you look at it in a physical fashion using volume fractions, here is your frozen fringe or an ice layer. Think about an ice layer on top of wet temperate firn, which is saturated. In that case, it doesn't matter what's on top. That will be offsetted by a contact discontinuity. And then this lower region, since there is no heat transport via conduction, there is heat transport only by advection. Water is not moving up or down at this point. So there is no fun happening, and that leads to a contact discontinuity. But that water nicely goes down as a self-similar spreading front called drying front. And it just goes down, and it will keep on going down with time. And that is the solution to this simple case 8, where you have cold, dry firn, or less dry firn, that not less dry firn, but cold and dry firn on top of temperate firn. Next, the case is where is the opposite, where we have a sudden rise in melt flux on top of cold firn. So in this case, we have a firn. The top layer is temperate. So this is temperate, this is cold. The temperature here is 0 degrees Celsius because we have liquid water, and it's 25% liquid water content, and 1 minus 0.8 plus 0.25 which is 0.45, 45% porosity. And in that 45% porosity, 25% is liquid water content. And the right state is 50% uh, porous, 1 minus C. There is no H here because H is less than 0. So 50% porous. And the temperature for this case is minus 15.84 degrees Celsius. And that will give you your enthalpy to be minus zero point 0.5. So this is your right state. So in that case, since they lie parallel to the fast path, you will go from top to bottom on this fast path. And it's an extended fast path because it goes into the cold region where in reality there is no path. This again goes in the direction where the speed of the characteristics decrease as you go from left state to right state. And that would lead to, again, a discontinuous solution. Or since this is Huguenot locus, we call it a shock wave. So there will be a shock wave or a wetting front in the cold region as a solution to this. So again, in the dimensionless velocity form, the solution is from top just a second. Although it may seem like this wave is not moving, it's moving at a very small speed. So let me start the slideshow again. So here, the wave is moving at a very small speed. It is moving down, but that jump is not high enough to have a wave which can move down. Bear in mind that as it goes down, it has to refreeze the surrounding, it has to warm the surrounding snow. And when it warms the surrounding snow, when it warms the surrounding snow, there is a slight reduction in porosity. So here, the porosity is the same up to this point, but then the porosity contours are like this. So there is a small reduction in porosity, small reduction in porosity when there is water that goes into cold firn. And that reduction in porosity happens because we need some of the water to be converted to ice to warm the surrounding snow or firn. In reality, this solution looks like this, where there is water infiltrating into the firn. Water is infiltrating to the firn, into the firn, and there is a small jump in porosity. But think about this. In this case, as it goes down, as the water goes down, the temperature here is 0 degrees Celsius, whereas the temperature in this case, in the right state, is about minus 15.84 degrees Celsius. So this is cold firn. This is cold. This is hot. So we need to refreeze a little bit of water to change the porosity or to warm the surrounding firn. We need some of the liquid water to be frozen and release that heat to warm the surrounding snow. And for this special case, that change in porosity after refreezing is the same change as your left state. So the porosity, it feels like the porosity is also moving along with this wave. And or the left state is just getting extended into the right state. But in reality, what's happening is we strike a perfect balance between the heat it is required to warm the surrounding snow, and that leads to refreezing of pore spaces. And that refreezing, this region, is exact same difference between the left and right state. So in some sense, it feels like your left state is just getting extended into right state, but that's not the case. That's a special case um, where this is happening. A more general case would be where there is a rise in melt flux uh, in cold Firn, and there is a step change in porosity. So here, the left state in this case is not saturated, but unsaturated Firn with 10% liquid water content, and 1 minus zero point 0.4 plus zero point 0.1, which is 0.7%, 70% um, porosity of the Firn. 70% porous, 10% liquid water content. And then the right state is cold Firn, which is 1 minus zero point 0.65. And uh, that is 35% porosity, 35% porosity. And the temperature is minus 19.5. If you plug in those numbers, it come out to be 0.65 and minus 0.8. So this is your right state. In this particular case, we do the same trick where we first go on slow path and then go on the right, the fast path. So we first go on the slow path in this direction, and then we go on the fast path in that direction. So that's our solution. And if we extend slow path from the left state and fast path from the right state, wherever they intersect, if it is less than C equals 1, which is fully saturated region, that is our intermediate state. So intermediate state here is this, 0.893 and 0.163. So here you have a contact discontinuity representing same meltwater flux, but different porosity in between left state and the intermediate state. But then from intermediate state I1, we have a fast path emanating into the cold region. So it's an extended fast path. Um, and since we are going in the direction opposite to the increase in the speed of the waves or characteristics, um, that leads to a shock wave. So this is C1S2 solution. So this looks like this, where you have in dimensionless velocity space, where from left state you have a stationary contact discontinuity here, where the meltwater flux stays the same, but the porosity changes at the initial jump. And then you have a right state where there is a shock wave that moves down. Bear in mind that colder the Firn is, smaller will be that speed, because you need to freeze a good amount of water, and that lost water will reduce the flux of the melt. So colder the Firn, smaller will be the speed of this percolation. So this is C1S2 with S2 going down. In a physical sense, this is the solution where the top state was again more saturated, and the bottom state is this cold Firn. And in this cold Firn, the temperature is minus 19.5, and the porosity is 35%. And then porosity is 35%. And then the water just goes into the cold Firn. But as it goes down, um, you form this intermediate region. So this is intermediate region I1, and this is your right or bottom state. This is your top state or left state. I'm using left and right because that's the norm in the community. And here you can see there is this initial jump uh, from contact discontinuity C1. And then there is a moving shock. And then you can see that this porosity is also changing because this part of liquid has to freeze since the temperature here is less than 0. So it has to warm the Firn to 0 degrees. And in that process, you lose a part of your melt. And that forms this increase in ice volume fraction. Next, we talk about the case where the left state cannot be left state. If you extend the slow path from the left state, it cannot intersect with the fast path from the right state at a case where C is 1. So this intermediate state is in unphysical region. What happens in that case? In that case, it first goes up. You just draw fast path from both left and right state up to C equals 1. And that is your saturated region. You're forming a saturated region. The flux is not enough in the flux is more than enough in the top layer, which could not be accommodated by your bottom layer. And once you extend it to the top, from there, you can just join them. And the solution in this case, again, similar to your temperate Firn, is S1 star, J2, and S3. And I won't go into detail of it. You can see how to calculate the speeds of these shocks. And it has two intermediate state, but this is identical case where the left state is saturated, not fully saturated, but unsaturated Firn, left state, and the right state is 50% porous. 1 minus C is 0.5, and this enthalpy equals minus zero point 0.1, which corresponds to minus 30 degrees Celsius. So you have temperate Firn over this region is minus 30 degrees Celsius, and the top Firn is saturated. So think about somewhere deeper into Firn where you see these transition. And in that case, you form a rising perched water table or a leaky perched aquifer, because there is still this wetting front S3 that will percolate into the Firn. So it's a leaky Firn. It's not a or leaky perched aquifer. It's not a closed like an aquitard. So again, the solution, as you have already seen, is from the left state L. You first have a contact this. You first have a rising perch water table S1 star, and then you go to a saturated region where C equals 1. In the fully saturated region, the composition stays, or dimensionless composition is 1. This is your first intermediate state, I1, this one. And then there is a jump in enthalpy because of jump in porosity. And then there is this state I2. Composition does not change because everything is water, either liquid form or solid form, but the porosity has to be accounted for in some form. So enthalpy takes that role. So this is I2, and this is the jump J2, and then from I2 to R, or the bottom state, there is a shock that moves into the cold region while it can refreeze. So this is different from the case number 6 because there is refreezing by this wetting front. So this is a new case we found through this work, which was not reported in the literature. Physically, the solution looks like this, where you have a wetting front that moves down at the interface. And since this lower layer is unable to accommodate this huge amount of water, this water is huge. The meltwater flux is huge. So um, in that case, the flux is greater than the saturated hydraulic conductivity of this region. And the wetting front bifurcates into two fronts. One is rising perch water table, and then there is a wetting front that moves down. And as it goes down into the cold, minus 30 degrees Celsius Firn, in that case, you refreeze as well, which is a unique characteristic for this case. And as it goes up and up, it can go to the top and cause ponding. Lastly, we end with the special case of formation of an impermeable ice layer through heat advection. This is different from the one we reported in our GRL paper because the impermeable ice layer here in this case is forming due to heat advection and not heat conduction. So in this case, if our right state lies in this triangle, And this triangle has a formula which is 1 minus C plus H in the right state is less than 0. If your right state lies in this, doesn't matter where your left state lies in this. I mean, I picked this value, but it could be any value. Think about any value. It does not matter. What matters is your right state, how cold your Firn is. If it is 95%, so it's composition, which is 5% porosity, and the temperature is minus 30 degrees Celsius. So this is minus 0.18. What I would say is pick any number, low porosity, cold Firn. In that case, you will form an impermeable ice layer straight off the bat. So the solution in this case is you go to this point from the right state. So it could be any point here in this region. You connect it to this point. One composition equals 1, enthalpy equals 0. You connect it to this point. And then from the left state, you go along the fast path. Since there is saturated region forming, you cannot form an ice layer without completely saturating. So you form a fast path that goes to C equals 1. That is your first intermediate state. You just extend it to C equals 1. And from the right state, you just connect that to this point, which is C equals 1, H equals 0, which means temperate ice without any liquid water or air. And then you connect, so this is your I2, and then you connect them too. So the solution in this case is S1 star. It's again a rising perched water table, but in this case, it's rising above an impermeable barrier. So it's like an aquitard. And the two intermediate states are connected by this jump J2, and the intermediate state 2 and the right state or the bottom state are connected by this contact discontinuity called C3. So the solution here could be just the formation of an impermeable ice layer. So you can see in this case, this is your left state, this is your rising perched water table. This is a non-leaky perched aquifer. There is no leakage because you are forming an impermeable ice layer. So here in this case, you can see that this is your first intermediate state. And then there is this second intermediate state at this point. And between second intermediate state and the right state, there is a contact discontinuity. So this is S1 star. And then this is jump J2 because it's in fully saturated region. And then there is a contact discontinuity C3. So solution looks like this. Let me erase the ink. So think about any amount of water on top of this cold, very cold, and almost close to pour close off. Firn, in this case, 5% porosity. You can think about Firn close to pour close off. And in that case, if you satisfy for the right state, 1 minus C plus H is less than equal to 0, in that case, water will infiltrate here and instantly you form an impermeable ice layer. Let me try to zoom it. You can see that there is an impermeable ice layer at this point, which means there is no flow of water. So the solution again is you have a rising perch water table S1 star. Then there is a jump, initial change in porosity jump, J2 at this point, and then this is the end of the Firn or the base of this infinitesimally thin ice layer is your contact C3, contact discontinuity. So that is the case where ice layer is formed pictorially, and we show this using unified kinematic wave theory. Now, I have summarized all of these cases. These cases could be combined, but now I would show then an example of validation against numerical simulation where we are combining these simple cases to form a slightly more complicated Firn. So think about a multi-layered Firn where you have two where you have two layers, bottom one and bottom two. Bottom one is 70% porous, initially dry, so the liquid water content is zero, and temperature is 0 degrees, and it's about 5 meters deep. Below that, you have 30% porous Firn, which is slightly less porous, no liquid water, and the temperature is minus 20 degrees Celsius. So it goes from depth of 5 meters to 10 meters, so it's also 5 meters thick. So now there is some melt event on top, which has made the liquid water to be 40%. The porosity is the same, so it's just some melt event which has made the top 40% liquid water content. What will happen in that case? I will show the simulation result first, the numerical simulation of the governing equations without heat conduction. So in that case, the first panel here on y-axis you have depth, and then first is your porosity. There is a change in porosity from 70% to 30% porosity, and the jump is at 5 meters. And then it is initially dry, but you supply 40% liquid water at the surface. So you will see 40% liquid water wetting front coming down. And then there is a change in temperature. Initially, the temperature up to 5 meters is 0 degrees Celsius, and below 5 meters is minus 20 degrees Celsius. So let me erase this and play the video. All right, if I go back, okay, let me go to the laser pointer. What's happening here is, oops. What's happening here is you have a wetting front that moves down, and that wetting front, you can see that that wetting front is bifurcated into two fronts. One go up and cause ponding, and one goes down while causing refreezing. You can see that there was no refreezing initially, but as you go into the colder regions, in this region, you can see that there is a porosity drop, and the porosity is dropping precisely because we want to reheat a certain amount of Firn in order to percolate through it. And that can also be seen through this change in temperature being propagated downward. It's sharp because there is no heat conduction. If there were heat conduction, that would have been diffused in some fashion. Now, if we combine the solution at all times, this is how it looks. Here initially, so on top you have porosity, liquid water content, and temperature. Initially, the porosity is 70% here, 30% in the bottom. And if we now focus at the middle plot, which is liquid water content, you could see that there is a wetting front that moves down. And as it reaches the point of transition where you transition into cold Firn, at that point, the lower layer is unable to accommodate that amount of water, and instead it bifurcates into two fronts. So one goes up as rising perch water table, and the other goes down as wetting front. What if I tell you that the contour plots are numerical solutions, but these lines are analytic solution, and that analytic solution comes from the same analysis we have been doing on the past several slides. So in this case, this is our top state, this inverted triangle, and the Firn up to 5 meters depth is bottom one state. So this is our bottom one state. And if you plot that, you can just connect them by a simple line that goes from this point to that point, leaving to formation of a shock wave or a wetting front. But as you start to go in this cold region, which is bottom two state, where the temperature is minus 20 degrees, in order to invade into that region, um, not all of the water can do it, first of all, since the porosity is small. So you bifurcate. So this bottom two is this state with bottom two is this state of C equals 0.7, so about 30% porous, and at a temperature of minus 20. So this is minus 0.088. In this case, we extend it to the case for C equals 1, and and then we connect them. So this is like case 11. So here you form first a rising perch water table, S1 star, and then this is jump J2, and then there is shock S3, S3, S1 star. And initially there was just S, right? So this is your entire solution. We don't have to run a numerical solution to know what will happen in Firn. And that's the beauty of kinematic wave theory. Moving forward, I would like to refer you all to table 2 of the manuscript. In that table, we have mentioned the cases, what kind of case it is. I mean, you have seen the video, but if you directly want to refer to the table, I would strongly say and suggest that if you don't have enough time to read the manuscript, just look through the table. Here, the region of the left state UL, which is just a vector of C and H, lies in second region, second region, second region. And then for the right state, this is second region or three-phase region, three-phase region, three-phase region. But then we have cases with air and ice region or cold region. So region 1 is cold region. So that gives you where the states lie, in which region. And then we talk about some of the state properties. What is the state property? What is the flux, or what is the composition? How is the composition related? So that is written in the state properties. And then we summarize the solution in 3 parts. First is the summary showing how the solution is, either it's a contact C, it's a rarefaction R, or it's a shock wave S, or it's a jump J. So how are these states connected to each other? That's mentioned in the summary. Then we summarize the equations that constitute the solution to that particular case. And lastly, we also talk about the construction figure, how to construct the solution, although it's pretty understandable after this video how the solutions need to be constructed once they are plotted on the hodograph plane. Then I talk about the physical relevance. How could one think about these weird mathematical solutions in a physical sense? And that is very important for us as glaciologists. Lastly, I end with some related works where people have either witnessed the same solutions or they have seen something similar to them and did not talk about it in much detail. So you can check those related works out as well. So with that, I'd like to summarize this lecture. In summary, unified kinematic wave theory can help analyze many problems in Firn just by good sketching skills. You don't need to run a code. You don't need to make your life miserable. You can just take a picture of hodograph plane and you can do some sketching based on what properties you have in the Firn. It helps predict formation of leaky perched aquifers and impermeable ice layers through refreezing. And that refreezing is caused by heat advection, not by heat conduction. We found that next simple cases could be combined to form complex problems, and that can compare well against numerical solution. I showed one example. I have validated all of the cases I showed here today. Lastly, these solutions can be used as benchmarks to validate and improve Firn hydrology, ice sheet, and Earth system models. So they can help us compare the performance, compare how we could model these solutions or improve these codes. Lastly, I want to say that the table 2 in the manuscript has a nice summary of all solutions. Please refer to that actively. And all the codes to generate analytic solution uh, are available on GitHub on this link. I will give the link in the YouTube video. But with that, I'd like to thank you all for listening to this lecture. For any questions, please feel free to reach out to me at mashadab@princeton.edu. And with that, I'd like to thank you all and have a nice day.